So every semester I forget to take this out. That point number 3, the histochemical techniques, ignore that, scratch it out, okay? You do not need to review any of that information for the exam. That's way outside our area of need, okay? All right, so hopefully this doesn't look completely new to you. We've got various levels of organization within skeletal muscle. And so we've got a combination of connective tissue and then muscle tissue, muscle fibers, all right? And they all coalesce into tendons at either end of the muscle, which is important for force transmission to the skeleton, right? The skeleton in and of itself can't move. So without muscle contraction and force production, and that being transmitted to the skeleton, we'd be like an amoeba, I guess, unable to move anywhere, right? So we have 3 layers of connective tissue that we want to be aware of. We've got the epimysium on the outside, wrapped around the whole muscle. Then we have the perimysium that is wrapped around fasciculi, and the endomysium that is wrapped around a muscle fiber. Okay? The muscle fiber is made up of myofibrils, and that's where we get our 2 proteins, our actin and our myosin. And they're going to play a big role in what we're looking at, because they're the point at which we use our ATP and we see muscle contraction occur. All right. The connective tissue, these 3 layers of connective tissue are important because they act to stabilize the muscle and support all these other components in their little bundles. All right, so just try to keep this idea of the bundles and the muscle fiber in your head, because when we talk about types of muscle fiber, then this picture here becomes really important to understand how we can have different muscle fibers within one muscle, okay? So again, another example, you can see here the connective tissue runs into the tendon, and then the tendon attaches to the bone. Not sure if you've had biomechanics yet, but Dr. Gira may have talked to you about this in structural kinese, that insertion point into the bone is slightly different for everybody, and it's one of the things that adds to our individual movement patterns and our individual ability to apply force, is the fact that mechanically the angle and the insertion can be quite different, all right? On the right here, this is an actual slide, all right? And so you can see the fascicle here, and then each of these little kind of almost circles is a muscle fiber, wrapped around by the perimysium, and then this whole thing would be wrapped around by the epimysium. All right? Okay, so we've already said that connective tissue kind of coalesces, joins together to form the tendon at each end. That's wrong. That shouldn't say epimysium, that should say endomysium. Helps prevent the spread of the signal for muscle activation. So when the nervous impulse comes to the muscle, we don't necessarily want to turn on every fiber within that muscle. So if we go back here, right, we might not want the whole thing to contract. So the signal may come just to some of these muscle fibers to contract, right? So the endomysium is responsible for preventing the signal from leaching into the fiber that's next door. Okay? And that gives us some control over this contraction. So when we did a little bit of motor learning and motor control, you know, and I'm always talking about the fact that the brain is sending these signals and controlling the amount of force. We're going to be looking at that here again. That's quite an important idea to understand, that to control force production involves controlling which, when, and how many fibers we turn on. Okay? So a coordinated movement pattern is partly due to the brain learning that grouping of, you know, which fibers do I turn on, how much do I turn them on, when do I turn them on, when do I turn them off. Okay? The connective tissue is somewhat elastic. It'll give a little bit, all right? And that's important because it plays a role. If you've been able to watch, or if you joined me yesterday for lab, we talked about the stretch cycle and the vertical jump, right? So the connective tissue is part of that, not the whole thing. We'll talk about some other things that play a role. So it's like a rubber band, right? If I stretch a rubber band and I let go, then there's a lot of force produced in that rubber band. So it's very similar to that idea, all right? So the stretch shortening cycle is a controlled eccentric action. So we said we're going to squat and we're going to stop before we jump on the vertical jump, right? So that elongation of the quadriceps is under control, and then we contract our muscle fibers and we shorten and we jump, right? If we do that without the pause at the bottom, then not only do we have the contraction of the muscle fiber, but we've got this rubber band action occurring from the connective tissue. Right? So that's one of the arguments for using plyometrics, particularly if you're a power type athlete, a sprinter or a triple jumper or something like that. Plyometrics are meant to train this kind of additional power, this additional force production. All right? If you look at page 80 in your book, there's a box 4.2, that talks about the impact of stretching on power activities. So there's been some research that says power is reduced if you do a static stretch before the power activity, okay? And they think that that's maybe due to a reduction of this rubber band effect because you've already stretched the connective tissue out. All right? I'm not saying don't look at that or read it or pay attention to it, but I would caution you the research I've seen is not very applied, right? So they're testing this power output under an extremely controlled condition. So they're doing a long static stretch, and then they're testing power. But I think when we look at an actual applied situation, right? And I'm a sprinter, and I stretch out my Achilles, and I stretch out my calves, and I stretch my hamstrings and my butt's a bit, right? And I shake up, and then I get into my blocks, and I'm in my blocks until the gun goes, and then I sprint. That's quite a long delay between the stretching and the power event. And a lot of the research isn't looking at that kind of timeline, right? They do the stretch and then they test the power, and they see a reduction in power. So I think it's certainly an area of research that is very applicable to us. Like, we would want to know that, right? If stretching is actually being detrimental to certain events. And it's something that's being looked at quite a lot right now. So I would just say, for yourself, dig into the research, right? Get into the library databases and look around for stretching and power type research if that's something that interests you. All right? Because, as I said, I think, I'm not saying it's not correct, I'm just saying I don't read a lot of ex-phys articles, remember, because this is not my area of study. So it may be that there's stuff out there that I haven't seen that is more applicable to a sporting situation. All right? Okay. So our sarcomere. So the sarcomere is the unit that end on end makes the length of the muscle fiber. So when you look at a muscle fiber, it's like little dominoes laid end on end to each other, okay? And the sarcomere is the smallest unit that can contract within the muscle, all right? So because of the layout of the protein fibers, the sarcomere is able to create force production, and it can shorten in length as it creates that force. All right? So if you look at skeletal muscle under a microscope, it looks kind of stripy, striated, and that's due to these protein fibers lining up kind of in parallel to each other. All right, so sometimes in some reference books, skeletal muscle is called striated muscle. If we look at heart muscle, it doesn't have that same kind of stripy look to it because the muscle fibers are laid out a little bit differently in cardiac tissue. So the key when you're looking at this diagram, all right, don't worry about titin, don't worry about telethanin, or even nebulin. The key that we're interested in when we look at muscle contraction is the fact that the actin fiber, which is the red thin line, attaches to the Z line, which is at the end of the sarcomere. Right? So this actin on this side is coming from the next sarcomere along. The big blue brushy looking fiber is the myosin. Right? It's called the thick fiber. It isn't attached to the Z line, and it isn't permanently attached to the actin, but they do line up alongside each other. Okay? But the fact that the actin on this side is attached to the Z line here, and the actin on this side is attached to the Z line, the other end of the sarcomere, is an important visual for you for when we're talking about muscle contraction. So those other proteins that are in that picture have an important role, obviously, otherwise they wouldn't be there. They provide like the lattice work, like the framework for the sarcomere, but they're not part of what we want to look at for muscle contraction, okay? They do provide an element of stiffness, so the muscle isn't just kind of collapsing on itself, right? So when the sarcomere shortens, the actin filaments are sliding across the myosin filaments, and because they're attached at either end to that Z line, they drag the Z line in towards the middle, and that makes the sarcomere shorter. All right, we've got some diagrams for that in a minute, and I think everything's always easier with diagrams. When the sarcomere relaxes, we don't uncontract the muscle, right? The muscle can only contract and shorten. There's no way of it contracting and lengthening, right? So what happens is the signal from the central nervous system that's telling the muscle to contract stops. And then as the muscle relaxes, it kind of just moves back out to its regular length. Okay? We rely a lot on the weight of the skeleton and on gravity to move the muscle back into a relaxed state. All right, so the proteins that we're interested in are actin and myosin. Actin is sometimes called the thin filament. So as you saw on that previous picture, the actin was the thin red line, right? And it's actually made up of 3 different protein molecules: actin, troponin, and tropomyosin. And they're all kind of interacting and entwined with each other. But the whole compound, I suppose, is called actin for simple reasons. So we have a helical twist of actin molecules, and on the actin molecule is a receptor site, all right? So you can think of it like a little blob of sticky honey or something, right? And that receptor site is the point at which the myosin head will attach to actin, which we'll get to in a minute, all right? The actin molecules are wrapped around by tropomyosin and troponin, all right? So when you look at this diagram, the green and yellow kind of rope is the tropomyosin, right? And the troponin is attached, and it covers up the receptor site. Don't worry about troponin I, troponin T, troponin C. All right, that's more detail than we need. Just think of it as a troponin complex. All right. Okay. So the myosin filament is sometimes called the thick filament. All right. And it's a really interesting protein. It's made up actually of protein and ATPase. So it's got this kind of globular double head on it, attached to a hinge joint, and then to a big, long, fibrous tail. Looks a little bit like a tadpole or a sperm, right? The head part is made up of an enzyme called myosin ATPase. So we've seen ATPase before, remember, in System 1, and when we're looking to release energy in the other systems as well. It's just we don't talk about it in the same detail there. But remember, in System 1, we said that 5 to 10 seconds at the beginning, we get energy from breaking down ATP and releasing that third energy bond with the help of ATPase, right? It facilitates, it speeds up releasing that energy from that third bond. So in this case, we have myosin ATPase. Myo, anything is to do with muscle, right? So we've got a particular ATPase in the muscle itself getting ready for contraction. Right? So this head is myosin ATPase. The tail kind of wraps around its neighbor and its neighbor's neighbor. So we end up with a thick filament with all these little heads sticking out of it, right? And the body of the filament is all the tails wrapped together. Right? So this idea of the head sticking out and the hinge joint attaching the head to the tail is important because that's where we get the shortening of the sarcomere from. So think back to, we've got this receptor site on actin, and under certain circumstances, the head of the myosin can attach to that receptor site on the actin, right? And then the head can move because it's got this hinge joint. Okay? Let's go back here for a minute. Questions so far? Most of this, I suspect, you covered either in AMP. I'm not sure how much of it Dr. Guerra will have had time to go into detail. But hopefully this isn't brand new to you all. Okay, so the ATPase plays an important role because there are several different types of myosin ATPase, and which type the myosin has dictates what kind of fiber that fiber is going to be. And by that I mean that we have different muscle fiber types. Okay? So, we have type 1s, which used to be called slow twitch fibers. I think that's an important thing to think about. But if you're digging around on the internet, if a site or a blog or something you're reading is talking a lot about slow twitch and fast twitch, they're either a little bit out of date or they don't understand the technical terms because they haven't really done XPhys, or they may be trying to simplify the verbiage for their reader, right? So you've got a couple of options there. But pay attention to what you're reading, right? Be critical. Do they know what they're talking about if they're using this term? Right? So type 1s used to be called slow twitch. Type 2s used to be called fast twitch. okay? And so the myosin ATPase dictates whether the fiber is a type 1 or a type 2. Is it slow myosin ATPase? Is it fast myosin ATPase? All right? The ratio of type 1 to type 2 fibers is almost completely decided before birth, and the ratio is completely finished by the time the infant is 1 year old, right? So that ratio of type 1 to type 2 is established at an age that we can't train it, right? It's done. We've got what we've got. It's genetically determined, and I have the ratio I have, okay? So type 1, on this diagram, type 1 is the orangey kind of line. So you can see that it's relatively slow, okay? Because this is in milliseconds, so it's not slow. It's just compared to type 2s, it's slow, right? Relatively slow to reach its top force. And the top force is quite a lot less than a type 2. Right? However, because that picture tends to go, well then why do we want them? Right? They are really, really good at using oxygen to make ATP. Okay, so our third energy system works very, very well in type 1 fibers. That means that they are pretty fatigue resistant, right? So unless we run out of oxygen, in which case we're in trouble anyway, okay, then I can pretty much keep contracting over and over and over and over and over and over and over, because I'm not producing any byproducts. Remember, we're only producing water and carbon dioxide, neither of which are toxic within the muscle cell. Right? Because the carbon dioxide gets moved out very quickly, and the water can get used or moved out. Right? So they're fatigue resistant, which means they're really good for aerobic performance or endurance events. Okay. Type 2 is the blue line, and by comparison, type 2 develop their force very quickly, right? Their peak force is much higher than a type 1. However, type 2s are not very good at using energy system 3 with the oxygen to make ATP, right? They rely much more heavily on glycolysis and ATP-PC systems, okay? That means they're producing the byproduct is something that can't stay in the cell and keep making ATP, right? We're producing those hydrogen ions, and we start to get an acidic environment, and sooner or later, ATP production drops through the floor, right? So our type 2 fibers fatigue very easily, right? But because of this ability to create such a large force very quickly, they're really useful for high-intensity, short-duration events like sprinting, throwing, jumping. Okay? All right. So normally now I write on the whiteboard, so now I have to try and do one of these. All the things in here. Okay, let's see if I can do this. All right. So, as I just said, the ratio of type 1 to type 2 is genetically determined. All right. So, an average person has a ratio about 50-50. Okay, whatever an average person is. So that means that this person could run a marathon, right? They have enough type 1 fibers to run the marathon. They're just not going to be great at it, right? And because it's 50-50, I've got enough type 2 fibers that I can sprint. It's just not very fast, right? So an average person gets to be average at running fast and running for a long time, okay? When we compare that to elite athletes, we have a different picture, okay? So let's look at an elite endurance runner. Okay. An elite endurance runner is going to have around anywhere from 70 to 85% type 1 fibers. So let's go with the high end of that, right? If I've got 85% type 1, then I only have 15% type 2. Okay, now that's the extreme picture. As I said, it could be 70-30. But 70-30 is very different to 50-50. Right? They actually probably, I guess, someone who was really good is probably more like 75-80, because they'd want enough type 2 fibers to be able to sprint ahead of the rest of the field at the end of the race into the line. So, all right, so very, very different genetic makeup, right? This is not training. This has nothing to do with their training, right? They've just been lucky enough to find a sport that optimizes their genetic makeup, right? What about when we look at an elite sprinter? Right? An elite sprinter is going to have 65 to 70% type 2s. So let's say 65, 70, let's give them 30% type 1 and 70% type 2s. So they've got heaps and heaps of these fibers that can generate way more power than a type 1, much, much more quickly, right? And that's why they're good at sprinting, jumping, throwing, right? All these short duration, high intensity events that need immediate, dramatic levels of power production. They're really good at that. Right? Now, the ratios are not equivalent all through the body. So that can be quite interesting, right? You might have someone who's got really high levels of type 1 fiber in their legs, but they're more average in their upper body. Right? So it's not, the ratio isn't set for every skeletal muscle in the body. Okay? So when we train these people, right, and they get stronger, we're not switching fiber types. We're increasing the size of the fiber they already have. All right, so we're using hypertrophy. We're seeing growth through hypertrophy because the fiber is getting larger and therefore stronger. Questions? While I'm getting us back to our PowerPoint here. Questions? All right, so we're going to finish on this slide and take a few minutes off because it's Friday afternoon and we've earned it. All right? I want you to ignore the information about type 1C, type 2C, type 2AX. Okay? And the reason I say that is that, to my knowledge, those muscle fiber types have not yet been found in human skeletal muscle. All right? In human skeletal muscle, type 1 is identified, type 2A is identified, and type 2X is identified. Now, that doesn't mean the others aren't there, right? But if they're there, we haven't found them yet. Okay? All right? So, I want you to think back to that cross-sectional picture we had at the beginning. Okay? Because here, when you look at these slides, now you can see what I was saying about how one muscle can have type 1 and type 2 fibers within it. All right? Because each of these is a muscle fiber. All right? The muscle is not type 1 or type 2. Right? The muscle fiber, the muscle cell, is type 1 or type 2. So the muscle itself, when we look at the entire organ, is made up of different type 1s and type 2s. And the ratio of type 1s and type 2s is going to dictate what that muscle is good at and not so good at. Does that make sense? Hello. Are you guys there? Did I lose you all?
No, I'm still here.
Okay. Anybody need me to repeat anything?
I'm good.
You good? Is that Molly?
Yes, I don't want to speak for everyone though.
Okay. All right, I want to stop here because I want to let this sink in over the weekend, because I think in some ways this is counterintuitive, because we get told over and over again that if we try hard enough, if we work hard enough, if we train hard enough, we can achieve anything we want to do, right? And physiologically, that is a big fat lie, right? If I have tons of type 1 fibers and what I want to be is a world-class basketball player, I'm stuffed. It's not going to happen, right? Because basketball players are fast and explosive, and I don't have the muscle fiber to be fast and explosive, right? And the other way, okay? If I've got tons of type 2 fibers and what I really, really want is to be a world-class marathon runner or a Tour de France cyclist, I'm stuffed. It's never going to happen. Okay? So I'm going to stop and let that soak in, because it is kind of not what we're told and not what we're taught training is about. Right? We're taught that training is about making me faster. No, it's about making you stronger. It's about increasing your neurosignals to the muscle. It is not about making you faster from a muscle fiber type. Okay? All right then. If there are no questions, I'm going to say ta-ra. Have a lovely weekend. The weather is supposed to be absolutely gorgeous. Please stay safe, wear your masks, wash your hands, socially distance. We are not winning the battle that we should be winning right now. This stuff should have flatlined by now, and it isn't. So do your bit, keep yourself safe, okay? All right, I'll see you on Monday.